vai fazer isso agora, não vai esperar. Não pode ser. A gente vai ficar assim. A gente falando agora, a gente vai transmitir, a gente vai estar pegando. Agora,
o James já tá?
Lá?
James?
Ah. Já tá. Gente, já tá. Eu também.
Hi, James. Do you hear us?
Yeah.
Hello.
You're fine.
Do you want to try to share your screen?
Yeah, 1 second. At the moment, the host has disabled participant screen sharing, apparently.
Try
Okay,
now.
I did now.
Michelle, o som tá saindo ali. Vamos ver aqui. Alguém sabe? What about now? Can you hear us?
I can hear you all right. I think
Okay.
it's working, isn't it? Hopefully.
Não. Clara, você pode falar um pouquinho para a gente ver o som de saída?
Oi?
Oi.
Eu
Fica
estou escutando bem vocês.
Isso, a gente te escuta, a gente só está querendo colocar o som na caixa de som maior.
Sim.
Aí, lá,
Tá me chamando?
pode ficar falando aí, a gente está testando o áudio.
É que fica bem baixo quando vocês falam longe do microfone.
James, we're trying just to get the sound to the proper system because it's going in the wrong system. Just a moment.
Yeah, let me know if I need to speak or anything. Help.
Okay, I'll introduce you first, so no worries.
A TI tá vindo. Eu ia dizer como sabe chamar Sim, eu percebi que não precisa a gente ir lá, é só ligar no canal deles.
Ah,
Esse problema nunca tinha acontecido. Eu achei que estava conectado direto, não sei, deve ser algum que eu deve ser meu contato. Lara, fala de novo.
Oi, teste. Funcionou
Lara,
agora?
speak for us to see if it's working, please.
Yes, it's working now.
Guys, are you hearing us?
Eu acho que tá, porque
I can hear you.
eu acho que a gente não mulher. Eu acho que agora o áudio, acho que aquela saída lá está funcionando. Essa de caixinha.
Lara, can you speak, please?
Hi,
We don't
it's
hear.
working. I'm speaking. Hi. Tudo certo com o áudio?
Clara, pode falar de novo.
Oi?
Oi, agora te escutamos.
Ah, que bom.
Isso agora.
Agora continua falando um pouco.
Eu não tenho o que falar, gente. Falar o quê? Oi.
Continua, Clara, a alcunha da Thaís, faz o quê mesmo?
Tô aqui cuidando se os gatos não vão brigar.
Okay, James, we are almost set to go. So I'll start introducing you. So today we have Dr. James Nightingale, who is an observational cosmologist at Durham University. So he works with gravitational lensed galaxies to study dark matter, galaxy structure, and the largest black holes in the universe. He leads the development of the Pi Auto Lens open source software for analyzing strong lenses. He is an advocate for using software as a platform to teach and has written Jupyter Notebook online lecture series on gravitational lensing and statistics. A cool fact is that as a spin-off to his cosmology research, James works in close collaboration with the National Health System of the UK, researchers adapting statistical methods developed for cosmology to cancer research as part of multiple innovative UK clinical trials. James, thank you so much for accepting our invitation. You may start when you're ready.
Yeah, I'll just check, is the sound quality all good still?
It's good, yeah.
All right, great. Yeah, so hi everyone, I'm James Nightingale. Thank you for the introduction. So I'm currently, as I said, a postdoc at Durham University, but I'm in the near future going to be moving 8 minutes up north into the real north of England at Newcastle University, where I'll be continuing a lot of the lensing research I'm about to tell you about today. So yeah, I work on strong lensing, and I'm going to basically give you a run through of what we can learn about galaxies, dark matter, and supermassive black holes using this observational technique. And I'll talk about the software I used to do this, and this is the flashy logo we made for the software. This starts to change. So yeah, strong gravitational lensing, in case anyone's sort of not familiar with this. Strong lensing is when we observe galaxies behind other galaxies. Can I just check, can you see my mouse cursor?
Yes.
Great. And what happens is the gravitational field of the foreground lens galaxy is so dense, it curves space-time in on itself, meaning that multiple light paths can trace from the source around the lens galaxy and into our telescope here on Earth. So a strong lens is when we observe a galaxy multiple times due to the curving of space-time. And this talk is going to focus on these sort of single galaxy strong gravitational lenses, where it's just one big galaxy responsible for the strong lensing. You can get lensing from clusters, from groups of galaxies. That's not what we're going to talk about today. And the redshifts involved, these are kind of representative of the sort of systems I'm going to be talking about. So lenses around redshift 0.5, sources around redshifts of 2. And when we observe these strong lenses, there's kind of two measurements you can make. There's two ways to analyze these systems and do science. What a lot of the literature does, what a lot of people did throughout the 2000s, let's say, is they'd measure a single quantity from these strong gravitational lenses. This quantity is called the Einstein mass, and it's the total mass, stars, dark matter, everything else, traced out by the cylinder that roughly overlaps the lensed source as shown here. So this big blue ring of light is a multiply imaged background source, and the Einstein mass is kind of the mass within this. Yeah, and it's in astronomy, we generally regard this as sort of the best mass measurement that we have. It's regarded as model independent. It's regarded as kind of a 5% precision. So, a very accurate way to measure the masses of galaxies. And the reason it's so accurate is kind of shown here. Basically, for each of these strong lenses, if you imagine we have the redshift of the lens, the redshift of the source, let's say we've got those from spectra, that means we know these angular diameter distances. We know the distance to the lens from us. We know the distance to the source from us, as well as the distance between these two things. So we kind of know, the configuration of the strong lens. Simultaneously, from high resolution imaging, like the Hubble imaging here, we have a very precise measurement of the distance from the center of the lens to where we observe the source. So we also have this distance here measured to quite high precision. And the only thing we need to therefore infer is the angle subtended by the lensed source's emission, which you can actually work out like very straightforwardly through Pythagoras at this point. Obviously, we use more intricate analyses to do that, but inferring this angle is not a difficult calculation. And the key point is once you know this angle, you therefore know the gravitational potential, the total mass in the lens necessary to curve space-time in accordance with the angle that's observed. So with a back of the envelope, you can come up with a pretty robust estimate of the lens galaxy's total mass according to general relativity. And so, yeah, lots of people measure the Einstein masses, this single quantity of lens galaxies, and they do science with it. For example, they might compare the Einstein masses to stellar masses from stellar population synthesis in order to test assumptions regarding the initial mass function of stars, which is great. But this isn't the type of strong gravitational lens modeling and analysis I'm going to talk about today. What my research focuses on, and all the results I'm going to show, actually try to extract a lot more information from each strong gravitational lens that we observe and study. So where does this information come from? Well, it's contained in the extended lensed surface brightness distribution of the background source. It's contained in each of these image pixels that we're observing to have traveled a slightly different path around the lens galaxy and into our telescope. And basically, if we can understand how these light rays travel to us on the Earth, we can make measurements not just regarding the lens galaxy's Einstein mass, but we can also infer how this lens galaxy's mass is distributed. So this is a different way to show how this observational technique works. Basically, we are observing light rays that all travel through slightly different regions of the lens galaxy's gravitational potential, as seen here. If we can understand how they traveled through the lens's potential, we can therefore perform a reconstruction of its gravitational potential and therefore equivalently its mass distribution at a very high fidelity. And so to try and give you sort of the numbers to sell you on this, in certain lenses, we're able to reconstruct the properties of their mass distribution at sub 100 parsec scales. So this is a really high fidelity probe of how the mass distributions of distant galaxies are configured, what they look like, basically. And this is the technique that I'm going to be basically presenting results on today. So in terms of the analysis, it basically means that we're trying to infer two things simultaneously. We're trying to infer the surface density or mass of the lens galaxy. This is an example mass distribution where we have lots of mass in the center or a high surface density in the center corresponding to the stars, and then not that much mass on the outskirts. And simultaneously, we're trying to infer what the source looked like before lensing. This is a reconstruction of a real strong lens's source galaxy where we've reversed the gravitational lensing in order to try and piece together what the galaxy originally looked like. And in this case, we actually reconstruct something reminiscent of sort of a face-on grand design spiral, as I guess you hope you would when you study galaxies. One thing to note is that you can see we're reconstructing the source here on like an adaptive Voronoi mesh that's reconstructing asymmetric light, it's reconstructing spiral arms. We have to reconstruct sources at this level of detail. We can't get away with using things like Sersic profiles, for example, because we have to very carefully reconstruct exactly how each of these light rays is traveling around the lens into our telescope, meaning we really have to understand the irregular and asymmetric morphology of our background sources. Couple of examples of how people, other people in the literature use this technique to study the universe. If you're familiar with the Hubble constant measurements via time-delayed quasars, this sort of technique is actually key to measuring the Hubble constant. So people use this to do cosmology. And of course, there's a lot of people who don't really care about gravitational lensing, or at least the mass distributions of galaxies, but they use this technique to reconstruct the distant, highly magnified source galaxies and study them. So this is a redshift-free galaxy that, thanks to this gravitational lensing magnification, we're actually able to resolve star-forming clumps at the orders of hundreds of parsecs, something that just simply would not be possible at redshift-free without this gravitational lensing effect. But I'm going to focus today on the mass distributions of the lens galaxies, and specifically what this technique can tell us about galaxies, galaxy formation and evolution, about dark matter, the dark matter particle, the nature of dark matter, and also how we can study supermassive black holes using this technique. Okay, so just quickly on the software analysis side, I'm not going to spend too much time on this. Obviously, as mentioned, I've developed for over a decade now, I've been developing this open source platform for strong gravitational lens modeling called PyLens. Everything's publicly available. If you're interested, check it out. There's a GitHub, you can just Google PyLens and you'll find all this. The one thing I'll emphasize, as said, I've got very into like writing Jupyter notebooks and lectures to teach people using AutoLens how to do gravitational lensing analysis. So these are really aimed at undergrads. They assume that you don't know what a gravitational lens going in is, and they'll teach you what gravitational lensing is, but also the statistics, the Bayesian inference necessary to do this type of scientific analysis. And we've actually had undergrads who took this course now have papers published using AutoLens. So they are an effective. They seem to be working. So yeah, if you're trying to think of a master's project or just interested, please check them out. There's a lot of time and effort went into these. This animation's not playing, so I'll probably skip over it. This was just going to be an animation showing how the lens modeling procedure works. But basically, it would just show that if we had a strong lens like this with these arcs, we'd eventually infer a gravitational lens model that looks like the data. But this animation's decided to not work. It's not a big deal. Okay. So the last thing I want to emphasize about the lens modeling analysis is obviously there's a lot of technical details about how this works that I'm really glossing over to focus on the science. But as I say, you don't need to know really how the methodology works in detail. But one thing we've really put an emphasis on has been automating this lens modeling procedure, doing this without any human intervention, because this is the only way we're going to scale up to large samples that are necessary to kind of have meaningful scientific conclusions. So my PhD student, Amy Everington, put out this paper where we basically did this. We took the largest sample of strong lenses to ever be subjected to this sort of detailed analysis, and we tried to understand how many of them we could analyze in a fully automated fashion. This mosaic is sort of the visual sort of representation of this study. So you can see the lenses on these columns, and then each of these are kind of their unlensed source reconstructions on these Voronoi meshes I showed earlier, showing the diversity of sort of galaxies we observe as strongly lensed sources. But the take-home point was, 59 doesn't sound like a large sample to a lot of astronomers, but in the world of lensing, this is a big lens sample, and we got a pretty good automation rate, crucially measuring all of the quantities I'm about to show the scientific results for. There were 5 systems that we weren't able to automate. We managed to make the measurements manually, but nevertheless, this was sort of reassuring that this procedure can be automated. Noting that with Euclid, which launched, I think 3 or 4 months ago now, we're about to have thousands of these strong lenses. So we are about to jump from 59 to probably 59,000 in the next 10 years. Okay, so as I say, what Amy did is she did this automated analysis of a large sample of strong lenses, and we measured lots of things about them that we then put together as some scientific papers that I'm going to give a run through of the results. And these results are really going to pertain to what this type of lensing analysis can tell us about galaxy formation and evolution. If we study the mass distributions of galaxies at this level of detail, how does that inform our deeper understanding of galaxy evolution? So this paper was called Beyond the Bold-Taylor Conspiracy, where we're basically studying the density profiles of our strong lens galaxies, the foreground galaxies doing the lensing. So the first question is, of course, well, what is the Bold-Taylor conspiracy? It's sort of a very important result from strong gravitational lensing, but maybe isn't totally sort of known in the wider community. But this result was basically one that people found in the early 2000s using a sample of roughly 100 strong gravitational lenses. And what they found was that the inner 10 kiloparsecs, the mass distributions within 10 kiloparsecs of 100 or so massive ellipticals were all remarkably similar to one another. They all had a density profile where this gamma value was 2, which basically meant that their mass distributions all corresponded to something that was very close to an isothermal mass distribution. And this is sort of a puzzle for 2 reasons. This plot shows it another way, where these are the individual density slopes of these 100 galaxies. So this value of 2 is an isothermal, and these are sort of the individual measurements of the 100 lenses. And the key point is there's not much intrinsic scatter here. So I always find the way I like to pose this as a very interesting observation is we're basically looking at 100 massive elliptical galaxies. These things have undergone God knows how many processes to get to the redshift 0.5 where we observe them. You know, wet mergers, minor mergers. There's AGN feedback that we know is critical for these things. In the high redshift universe, they're being built up from potentially hundreds of mergers. And yet, whenever we observe these massive ellipticals in the nearby universe, they all have pretty much exactly the same mass distribution within the inner 10 kiloparsecs. So why is it that galaxy formation is so predictable? Why does it always lead to massive ellipticals that on certain scales are so similar to one another? And this is sort of, it's still, I'd say, a bit of an unknown, or this is sort of something that's very much an active study, area of study. The other way to pose the bulge halo conspiracy as interesting is, of course, to look to cosmological hydrosims of galaxy formation and understand how this density slope measurement, this gamma coming out very close to 2, how it can inform us about how to form galaxies. So in this study, Wang et al. In 2019, they went to Illustris, which is a big cosmohydrosim. They found all of the galaxies that they believed were representative of strong gravitational lens galaxies. And they studied how this density slope parameter gamma changes depending on the feedback mechanisms or prescriptions of the cosmological simulations. So, you know, there's different ingredients here, but the obvious one is this one. If you switch off black hole feedback in your simulation, so you don't have AGN blowing out large amounts of material, which we know is key to forming massive ellipticals of the right size. Another consequence is that your density profiles, instead of being around the observed value of 2, become much higher. This means they become much more concentrated than the observations. And so what we learn here is that black holes and the feedback that blows material out is key to not just forming galaxies of the right mass, but forming massive ellipticals with the right mass distribution to match the observations. And there's lots of other, you know, as you study this in more detail, these sorts of strong lens observations can start to allow you to discriminate between different types of black hole feedback and so forth. I'm not going to go into the details of this plot anymore. The key point is these observations are really critical to deciphering how to form galaxies of the right size and mass distribution. But the bulge halo conspiracy, the results I just showed in those 100 massive ellipticals, they were not observed from a lensing analysis like this. What the authors did was they measured the Einstein masses, the simple quantity I described earlier, and they combined those Einstein masses with simple stellar dynamics models of the galaxies, which was kind of an independent measurement of its mass. And so the question myself and Amy asked in this study was, if we do away with the dynamics, which is a very important thing to do, as I'll emphasize in a moment, and try to measure these mass distributions, these slopes near isothermal using just the lensing, using the way I described earlier, do we get the same result? Can we measure this quantity that the previous studies measured in a way that doesn't use dynamics, using this lensing only technique? And so this is exactly what we did. This is sort of a similar histogram showing the distribution of these density slopes. And this is for 48 strong lenses where the measurement of these density slopes was available both from previous studies that used the lensing and dynamics compared to our lensing only measurements in purple. And at a sample level, we basically find in these 48 lenses, we perfectly reproduce the bulge halo conspiracy results from the 2000s. We get something, again, very close to isothermal with a relatively small amount of intrinsic scatter. So we once again see there appears to be this sort of homogeneous nature to the way the strong lenses are forming their mass and distributing their mass within their inner 10 kiloparsecs. We attempted to do a kind of one-to-one comparison between the slopes of previous studies with the slopes of our lensing only measurements. There seems to sort of be a correlation, but when you dig deeper into this, you can't really learn too much about this. Basically, the error bars typically on the dynamics are so large that it's basically there's not enough statistics to say whether these two samples are drawn from the same distribution. So people like to see this plot because it's an obvious thing to look at, but we need larger samples to really assess if the two measurements that are meant to be independent agree with one another. Another key thing you can look at, which informs galaxy evolution studies is to look at whether these mass distributions, these slopes, are changing as a function of redshift. So I've cut off the x-axis here, but this is lens redshift on the x-axis. And what we can see is there's effectively no correlation between the redshift of the lenses and their density slopes. And studies have shown that this basically indicates that from redshift 1 onwards, lens galaxies are not changing their mass distributions as they evolve through cosmic time. So whatever this power law slope is at redshift 1, we believe that's roughly what it's going to look like in each individual lens if it evolved to redshift 0. But we do find correlations with other properties. So this is the total mass density of our lenses. And we find that for the lensing plus dynamic studies, we indeed find that galaxies with a higher density slope indeed have a positive correlation with their total mass density. Now that's, if you pause for a second, you think, well, that's a really obvious result, because surely if a galaxy has a higher total mass density, it's going to have a higher density slope. There was nothing surprising about this correlation when the authors in the 2000s uncovered this correlation. Where it becomes a puzzle is the exact same plot, if we now look at our lensing only slopes, has an anti-correlation. At face value, this seems to be saying that galaxies with a higher density, with a density slope that means there's more mass in the center, have a lower total mass density, which does seem like a bit of a paradox. I'm not going to go into the details of how we reconcile this, but basically it comes down to the fact that the lensing only measurement isn't measuring the density of the galaxy from 0 kiloparsecs, but it's actually measuring it where you observe the lensed source. So it's actually measuring the density slope in a regime of around 5 to 10 kiloparsecs, which actually means that this anti-correlation is something you would expect. So the only reason I'm showing this is to really highlight that there are differences between these two methods that, if you combine them, would allow you to understand galaxy mass distributions at an even more fine-grained level of detail. Okay, so that's the little part of this talk on the bulge halo conspiracy. And I want basically the two take-home points from this as follows. The key result of this study, the reason we did this, is that we demonstrated that we can make these measurements about the density slopes or the mass distributions of galaxies without the dynamics. Because dynamics is expensive, it doesn't scale to high redshift, it's simply something that we wouldn't be able to amass for large samples. Because we can make this measurement with just imaging, that means we're going to be able to make this measurement with the tens of thousands of strong lenses Euclid is about to find. And we can therefore start using this technique to actually constrain galaxy formation and evolution models at a meaningful level. We need thousands of galaxies to have the statistics necessary to actually use this to learn about galaxy formation. So that's the first key point. The second key point I want to make is, which I touched on earlier, is that measuring galaxy mass distributions in this way is not just more information on how to build galaxies, how to form galaxies in simulations. I consider it orthogonal information to the types of things our models of galaxy formation are traditionally calibrated on, i.e. the stellar mass function, the size-mass relation. These mass distributions really tell us information that we aren't currently calibrating our simulations on, and therefore they can provide us the sort of information necessary to, for example, control carefully how to set the AGN feedback in order to form galaxies with the right types of mass distribution. So I really think there's a bright future for using this type of observation to ultimately improve our cosmological hydrosims of galaxies. But there is a caveat: things are about to get a little bit more complicated. Which comes back to Amy's third paper she put out in her PhD, which was titled as following. It's a bit of a provocative, controversial title. Strong gravitational lensing's external shear is not shear. This is an intentionally provocative title, but I think we warranted. I think we were justified in doing this. So what's going on with this paper? What's going on with this study? So what is the shear? If you're not a lensing expert, if you're not clear what the shear is, I'm going to sort of present this talk in a way where you don't need to know what the shear is. So it really doesn't matter. It's not going to be important to your understanding. But just to be clear, shear is like the established quantity that we are trying to measure in weak lensing. These surveys, these stage 4 cosmology surveys that are going to measure cosmological parameters to incredible precision, they're effectively trying to measure this shear in millions of galaxies. The take-home point is this shear is therefore a very well understood quantity, theoretically, and we have a very clear understanding of how large the magnitude of this shear should be in different cosmological environments, in different parts of the universe. And I'm going to come back to that point in a moment. And it's very common for strong lens models to include this shear component as a standard. Pretty much every strong lensing analysis you'd read in the literature includes this as kind of a couple of extra parameters on the lens model. What people believe this external shear is modeling in a strong lens analysis is they believe it's kind of representing the perturbations of all of the line of sight galaxies surrounding your strong lens. So all of the galaxies to the north of the lens that are sort of well outside this region, they do contribute to the lensing. All of the galaxies to the south of this lens, they contribute to the lensing. In 3D, everything around the lens is contributing to the strong lensing, but we believe that these line of sight perturbations that they induce can be reduced to a simple external shear term. That's sort of the conventional wisdom of the literature. And what this study, mine and Amy's study we're about to show is that this is completely wrong. The external shear does not, in strong lens models, the external shear does not represent the lensing of line of sight galaxies. It's a complete fabrication of the literature that people believe this is the case. So now let's, given I'm making these quite provocative statements, I should probably show some evidence to back up what I'm saying. And I kind of have 3 lines of evidence as to why I kind of know that these external shears in strong lens models are not due to line of sight galaxies. First of all, in many strong lensing studies, the magnitudes of the shears that I myself were measuring, but also many other studies in the literature, were above a value of 0.05. Basically, if you ask any weak lensing expert, they will tell you that such a large value is only possible in galaxy clusters comprising thousands of galaxies. You need a huge amount of mass to produce a shear this large. It's simply not the case that you're going to measure a shear so large in field massive ellipticals, the sort of things that I study. So to verify this, Amy took her 48 strong lenses that she had measured the shear. I've got the strong lensing measurement of one of the shear components here. And we can see, as I was alluding to, many of these shear measurements exceed 0.05, which indicates there's something amiss. But Amy independently did a weak lensing analysis of these 48 strong gravitational lenses, which would therefore make a weak lensing measurement of the shear independently, and there's no correlation. So whatever the shear is that people are measuring in strong lensing models, it is not what they believe it is, because it just does not show up in the weak lensing. If it was due to line of sight galaxies surrounding each lens, the weak lensing signal would know about that, and there would be a much tighter correlation here. The only time there is this hint of a correlation is when the shears are at 0. So that's not a correlation. That's just these are objects that don't have that much shear. But there's a third line of evidence that actually starts to not only kind of demonstrate that these shears are not what people thought, but actually starts to give a hint at what the shears in the strong lens models are actually representing. So this visual will hopefully come along. Basically, a mass model for a lens, let's say an isothermal mass distribution or a parallel mass distribution, we basically consider it as like an ellipse or a surface density ellipse. It's an ellipse of mass that kind of decreases as a function of radius. And that ellipse has a single axis ratio, and it also has a single position angle. So if our mass distribution had a position angle of 0 degrees, that would mean it would be an ellipse that's aligned with the x-axis, as shown here. The external shear also has a position angle. The average sort of shear, if you considered it to be line of sight galaxies, it would be a shear position angle of 45 degrees would mean that there's an excess of line of sight galaxies at this sort of positive going in this direction here. So both of these quantities have an angle that we measured, Amy measured for all of her strong lens models. And if the shear were truly external, if it was due to line of sight galaxies that were completely decoupled from the foreground lens, the position angle of the shears would show no dependence, would show no correlation with the position angle of the mass distributions. It's kind of simple as that, really. And there's no reason why the galaxies surrounding this thing should be correlated with its internal mass distribution. Such correlations do exist, but they're a very faint statistical signal, so we wouldn't see it on such a small sample of galaxies for anyone who's privy to that. So when we take the difference of the position angles of our mass models and our shear models, and we plot them, sorry, I just pushed the wrong button there, as a function of shear magnitude, we can see that above this kind of threshold of a magnitude of 0.05, we have a high number of galaxies where the shear aligns with the mass model. So galaxies where the shear is preferentially going to the exact same direction as the mass model. So here, if the mass model had 0 degrees, these shears are also going to 0 degrees. That would suggest that all of the line of sight galaxies are perfectly aligned with its mass. But we also get a smaller fraction of galaxies that are anti-aligned, where the position angle of the shears and the mass models are 90 degrees offset from one another. And equivalently, we find that it's basically, it doesn't happen that if you have a high shear magnitude, that the shear is within 60 to 30 degrees of the mass model. So basically, and one thing I'll mention is someone independently from me gathered up all the lens models from the literature and remade the plot I just showed you. So this is like independent of anything I did, and they sort of reproduced this result in a more general sense. So I was very glad when I saw this, because it meant that someone had independently reproduced this result, that given how provocative I was going about the title and we chose to write the paper, it was a relief to see that this came through as an independent reproduction. Okay, so basically the summary here is the external shear that people are putting in their lens models shouldn't align with the internal mass distribution. This basic assumption of strong gravitational lensing is basically wrong. And what we believe actually is going on is that the external shear we're putting in these models is actually mopping up or accounting for missing complexity in the lens galaxy's internal mass distribution. So we're beginning to study the mass distributions of lens galaxies at a much higher level of detail, and we're finding that these shears that we're measuring correlate with all sorts of complexities, things like the mass distributions of the lens galaxies twisting as a function of radius, and the ellipticities of the lens galaxies varying as you go outwards radially. There are lenses where there's sort of offsets in the central mass distribution. For people familiar with boxiness and diskiness, sort of the studies of the isophotes of massive ellipticals in the nearby universe, there's a strong indication that these types of features are also what the external shears are mopping up or calculating. So the real conclusion here is, if you don't have a very complex mass model that's able to capture these very complex features, you'll get this kind of superfluous or anomalous shear measurement. So to wrap up this section of the talk, at the moment, this is a systematic. It kind of maybe sounds a bit negative, but the way to flip this around and put this as a positive is it means that even the strong lenses we've found so far, they contain a huge amount of untapped information on the very intricacies of galaxy structure. They're going to allow us to measure the boxiness and diskiness and mass twisting and all sorts of sort of azimuthal complexity in galaxies at high redshift that we otherwise never would. And maybe, just maybe, some of these features are actually in the dark matter, and therefore are going to allow us to start understanding the details of the dark matter halos that host these lens galaxies. But in order to get there, we're going to definitely need some advances in lens galaxy mass modeling. We're going to need to improve our techniques to, if you will, turn this systematic into an actual science result. Okay, so I'm now going to shift gears to dark matter. I'm overrunning a bit, but I'll speed up to make sure we stick to time. We're going to go away from galaxy formation and evolution. We're going to go away from studying the mass distributions of galaxies. We're now going to try and constrain the nature of dark matter, specifically the nature of the dark matter particle. So we're all probably aware dark matter is this material that only interacts with gravity. It's completely invisible to our eyes. We believe it makes up approximately 85% of the mass of the universe, not including dark energy. And we have a problem from a theoretical physics standpoint. We don't have a fundamental physics explanation for what dark matter is. On the contrary, we have lots of viable dark matter candidates and dark matter models, whether that be cold dark matter, so sort of the weakly interacting massive particle mass range for the dark matter particle, or things like warm dark matter, but also becoming popular are things like fuzzy dark matter, the ultralight dark matter models that we're seeing more in the literature. So how can strong lensing make observations that's going to allow us to hopefully begin to discriminate between these different dark matter models? Well, they make a key prediction about the universe's structure that strong lensing can test. So in a CDM universe, there's lots of dark matter structure. We can see that this is an image of a CDM, a dark matter simulation. And I'm sure we've all seen it before. And we can see there's lots of little pink clumps, which means that lots of low mass dark matter substructures form in our cold dark matter universe. In an alternative dark matter universe, here pictured as warm dark matter, these clumps do not form. Below a cutoff mass of roughly 10 to the power 9 solar masses, alternative dark matter models do not form dark matter halos, and therefore this is a testable prediction that would allow us to discriminate between different dark matter models and potentially even produce evidence that could rule CDM and therefore lambda CDM out. The problem is these things are such low mass that we can't observe them. They don't host galaxies because the galaxies basically have star formation quenched at these low masses due to the UV radiation background. These masses are slightly below sort of local dwarf galaxies. So we don't know if these things exist. We don't know if dark matter structures of order 10 to the 9 solar masses and below are present in our universe. But the key point is this technique with strong gravitational lensing can allow us to make this inference, because if one of these dark matter structures happens to align with the light of a lensed source galaxy, it perturbs its light ever so slightly, but nevertheless in a unique and observable way. So we can study these lenses, we can look for small perturbations to their lensed emission, and therefore try to infer the presence of these dark matter structures. And indeed, this is not sort of a new technique. It's actually over a decade ago that the first dark matter substructure was successfully detected in a strong gravitational lens observation. So this is the Hubble Space Telescope imaging of a strong lens where a dark matter structure of order 10 to the 10 solar masses is now established to be located near the arc. And so 2 dark matter structures have been observed using this technique so far. They're both too large in mass to constrain dark matter cosmologies, but they're the hint that this will work if we can just keep getting more lenses and analyzing them into more detail. So this is sort of the result from my paper where I reproduced this statistically significant detection of a dark matter substructure from the original paper. I'm gonna maybe skip over this in the interest of time. Let me just assess how to. So yeah, I will skip over. Sorry, the dog's now going crazy. Okay, so I'm going to talk about this study very quickly, where basically I decided I wanted to find or try and find these dark matter structures in HST imaging of 54 strong lenses. This includes the one I just showed, which was a known detection. But the long and short of this study was that in the other 53 strong lenses, we didn't detect anything. We got 53 non-detections, which sounds frustrating, but is actually kind of what you expect in a CDM universe. So the one thing I want to emphasize kind of relates back to the results I was talking about mass models not being complex enough. There were 4 strong lenses where I fitted them with kind of a simple mass model, the elliptical power law with a shear I described earlier. And I detected a dark matter substructure in the vicinity of the lensed emission here. But when I then fitted a more complex lens galaxy mass distribution, so one that decomposed the lens galaxy's mass into its stars and its dark matter, my dark matter substructure detection went away. This is not a statistically significant Bayesian evidence. And so building on our understanding that these shears are potentially a result of our mass models being too simple, we also now learned from this study that if you fit too simple of a lens galaxy mass model, you will inadvertently think there are dark matter structures that are there when they're not. And that's because the dark matter substructure is once again mopping up or accounting for the missing complexity in our lens galaxy mass models. And we've sort of dug quite deep into the mass distribution of this specific lens galaxy, studied its stellar light, the foreground emission of the lens, and we've sort of deciphered that there are the sorts of things we were worrying about earlier in this strong lens. So specifically, there's very clear evidence for the mass distribution twisting as a function of radius, which we believe is what is a result, is what is the complexity that causes this false positive that we then successfully model with the more complex model. We get lots of non-detections. The main summary of the non-detections is, in a warm dark matter universe, the result would actually be that we detect nothing below masses of 10 to the 9 solar masses. So we're not suggesting that we're in a warm dark matter universe yet. We've got a long way to go. But the key point here is that in order to make this a meaningful cosmological detection or result, we need to be able to scale up to hundreds of lenses, get hundreds of non-detections, and then demonstrate that we would have detected something in a CDM universe. And I'm not going to talk about how we're doing that, but that is very much sort of the direction we're now going. So on this dark matter stuff, I kind of had to rush through it because I've not timed this great, but we've been working on this for 7 years, longer than 7 years, and we haven't really got all that much to show for it. We don't have any meaningful constraints on dark matter, and we've really just been bashing our heads, failing to model lenses to the level of accuracy and precision necessary. And this has been a very frustrating time for a while, but the good news is I'm now feeling quite optimistic that we're not too far off being able to do this dark matter science with strong lenses, because I think we've made the key theoretical breakthrough that's going to allow us to do this. So this is another student at Durham leading this, Chuhan He. We've developed a technique that basically decomposes the stellar light and mass of the foreground lens galaxy into roughly 100 Gaussians using a multi-Gaussian expansion, a common technique used in stellar dynamics. And the key point is this can therefore capture, at least in the stellar mass, which is the majority of mass, all of these nasty complexities in the mass distribution we're currently failing to capture. This is able to capture twists in the mass distribution. It's able to capture variations in the ellipticity. Although I'm not going to show any results, we're seeing that this is actually allowing us to remove these false positives and therefore make a much more robust inference on the dark matter substructures. So we're working on this a lot, but I'm feeling really positive that we're going to have some pretty competitive dark matter constraints within the next couple of years. But we really have been struggling to make this theoretical breakthrough for a long time, but I think we're finally there. I'm going to quickly mention we're now finding lots of strong lenses with the James Webb Space Telescope and the Cosmos Web Survey. So I'm leading the effort to do this. We've got about 15 definite strong lenses with like incredible James Webb Space Telescope observations, and probably many more to come. And we also have a huge effort to do interferometer analysis in the UV plane using tools like ALMA for this dark matter substructure, where we basically built the methodologies necessary to do things fully in Fourier space in terms of how you do the modeling and analysis, which is sort of key to actually doing the dark matter science correctly. So yeah, on the dark matter side, watch this space. We think we're going to have some really interesting and key results coming, but I've been saying that for a long time. So hopefully in the next few years, we actually will. And this will be helped by these incredible Webb lens data sets that we're building up. Okay, so I've got on my timer, I think I've got like 3 minutes left. So I'm going to blitz through the black hole result in 3 minutes. Okay, supermassive black holes, why are they important? So this is a paper where I claim the detection of the first ever black hole in a strong gravitational lens. Black holes are really important, as I'm sure we're all aware, because their masses, the black hole masses, strongly correlate with many galaxy properties, most notably the velocity dispersion of the host galaxy bulge. So there's this strong indication that the black holes and the galaxies co-evolve with one another, which is kind of seemingly confirmed by cosmological simulations that need these black holes to form galaxies of the right masses and sizes. The problem is measuring black hole masses is really, really difficult. In the local universe, we can do things like study the radial orbits of stars that speed up when they go past these black holes, and therefore this allows us to kind of work backwards to the black hole mass. We can get sort of roughly 100 black hole mass estimates using this technique or similar techniques, but we can't really do it much further out. So this is as good as it gets for the local universe. In the high redshift universe, we can measure black holes for a reverberation mapping technique, basically studying the emission from active galactic nuclei. And this allows us to kind of, again, work backwards to the masses of their black holes. But it's, again, limited. We've only able to measure the masses of black holes in actively accreting galaxies. So it's, again, very limited, strong selection effects. Wouldn't it be great if we could measure the masses of supermassive black holes in galaxies that were not active? That would really fill in a huge amount of our understanding about how galaxies and their black holes evolve and correlate with one another. And so that's obviously, okay, can you see a YouTube video playing? just to check.
Yes.
Great. Yeah, so I'm going to end by just showing this YouTube video. So yeah, this paper, we're basically claiming that we have successfully measured the, detected and measured the mass of a black hole in a strong lens for the first time. So this was something we made for the public, but yeah, basically this is a strong lens. And what we're going to see is this lens has this giant arc, which is wonderful. And typically in lensing, it's the sort of thing we will look towards to it's aesthetically pleasing and nice. But what's really important about this strong lens is not this giant arc. It's the counter image that we're going to zoom in on now. This counter image is approximately 1 kiloparsec away from the center of the lens galaxy. And it turns out if you take a 10 to the 10 solar mass point mass, i.e. a black hole, the deflection of light, roughly a kiloparsec from that black hole, will be larger than the resolution or the pixel scale of the Hubble Space Telescope. So we anticipate the lensing effects of this black hole, if it's big enough, should be observable in the lensed emission of this counter image of this source. And so that's basically the premise of what our lens modeling and analysis did. What we find, which is going to be showed in this animation, is when we don't include a black hole in our lens models, we produce images that just can't quite reproduce the counter image, or they're offset. They don't do a great job. But as we increase the mass of the black hole in our lens model, obviously all of this is being done with the full auto lens framework. There's a huge amount of sort of proper Bayesian inference going on in the background. We start to produce images in our model that actually look like our counter images. But when we make the black hole too high, now going up to 80 billion times the mass of the sun, we again found that we overshot and didn't get a good counter image. And the premise of this result is you need a black hole somewhere around 33 billion times the mass of the sun to produce a counter image that looks like the observed data. I'm gonna therefore, I had a few more slides on the black hole result, but it's not all that important. So I'm going to finish by stating my summary and conclusions. Yeah, and I've told you how we can use strong lensing to study these different things. We've got about 100,000 of these strong lenses coming in the next year, 5 years. So all of the science I've just talked about is about to be done on an industrial scale. So I'm really excited about how strong lensing can hopefully contribute to our understanding of everything over the next 10, 20, or hopefully many more years. Cheers, and I'm happy to take some questions.
Thank you very much, James. So now let's open for questions from the audience.
Hi, James.
Can you come closer by
Yeah.
to the microphone?
Hi, James. Can you hear me? Yep. So
Yep.
I have maybe a technical question, because it seems that the major problem with current strong gravitational lens modeling is the simplicity of the models, and we talked this in the conference that we went together. But I want to know how much complexity can we introduce in your models without overfitting our data? Because we have some limitation in signal to noise and in resolution. So how much complexity or how much parameters or how much substructures can we introduce without causing this overfitting?
Yeah, so I'll say first of all that as we are making our lens models more complex, as we're kind of advancing in that direction, at least at Durham, we're always doing this within the framework of Bayesian model comparison, or some sort of framework or statistical method that allows you to assess whether you're making the model more complex and it's justified by the data. So indeed, in low signal to noise observations, we typically find that the models are good enough. And if we try to fit more complex models, they don't really change our inference. But in the very high signal to noise observations, that's where we're finding that these sort of complexities in the mass model, accounting for things like the mass twisting, is necessary, and it's justified by the data. We can sort of visibly see and statistically see that we get these improvements on the overall fit. So you're right that I think the complexity that we can add is ultimately driven by the quality of the data that we have on hand. The final thing I'll mention that maybe is also important is the MG approach, or the 100 Gaussian sort of approach that I showed a moment ago. This actually is trying to get around some of the concerns you had, because, or you might have, because this is actually using the emission of the foreground lens galaxy in order to effectively try and constrain the stellar mass distribution. We allow the mass to light ratios to vary, but the two-dimensional distribution is being informed by the lens light. And this is information that no previous lensing studies have exploited. So the other key point here is the sort of direction we're going is to try and add this complexity, but in a way where we have lots and lots of information left on the table in order to do that.
Okay, great, thanks.
Now we have another question here.
Hi, James. Congratulations on very nice talk. I have a question. I think that what happened with that, but no problem. No problem. I think that is the other side. But the question is the following. What do you think, or what is your opinion about that? For example, obtains massive or supermassive black hole troughs, the successive mergers of primordial black holes. Thinking, for example, in hierarchical model, or proposed to, for example, dark matter density of the universe.
I didn't fully capture the question. If you could repeat the key.
Okay, you have primordial black holes as theoretical assumption to explain, for example, some part of dark matter. Yeah. Okay, but for example, you can have the possibility to obtain, for example, massive or supermassive black hole troughs through the mergers, successive mergers of primordial black hole throughout the history of the universe, for example. What is your opinion about that?
I don't think I have a strong opinion in terms of primordial black holes as a dark matter candidate. I think they seem still viable, albeit they're sort of disfavored at the moment. They are potentially something that this type of lensing could constrain one day, albeit you'd need much higher resolution observations than we currently have. In terms of how they like, I don't have a strong opinion about how they would relate to as one mechanism to form supermassive black holes versus any other. I think, to me, my assessment is that really is like there's different models. We don't have the data of the observations to really discriminate them, and that's probably what these sort of deep web surveys pushing up to the really high redshift galaxy formation might inform. But I don't think my results and my analysis can really offer too much on that regime.
Okay, I understand. Thank you.
Any more questions from the audience? Augusto, or from Zoom?
Can you hear me?
Maybe not. Come close.
Just about, but come closer. Yeah.
We should stop being lazy and use the microphones, but then there's more that can go wrong.
Can you hear me now?
Yep.
When you are reconstructing the launched galaxy, what are the main sources of uncertainty? And how accurate do you expect your launched galaxy to be in general?
Yeah, so I've obviously intentionally glossed over the details of how we produce source reconstructions like this. And this is underpinned by there's a lot of linear algebra, Bayesian inference. You're sort of reconstructing this source in a way where you're trying to best fit the data whilst doing it in a way that isn't overly complex. So I mean, I'm not going to go into the details, but there is a lot of stuff going on underneath the hood here. But what I would say is, first of all, when people have looked into how robust or reliable these types of source reconstructions are, they really do seem to work really well on these galaxy scales for like most science cases. I would state with confidence that most people could use these reconstructions and reliably study the source galaxy, and I don't think it would impact on most of the types of science cases that people would want to do that if they're studying how star formation occurs, on what scales it occurs. I really do think, like in lensing, the source reconstructions, they really are one of the most reliable and sort of least subject to systematics aspects of what we do, at least on galaxy scales. If you pushed me and really wanted me to say, well, what is the biggest uncertainty here, I think it again comes down to the mass models. So if your mass model is too simple and has all of these problems that I alluded to in this talk, that will ultimately mean that the way that you're ray tracing the light back to the source plane to produce this reconstruction will also be somewhat inaccurate, and that will ultimately manifest as an inaccurate source reconstruction. But those effects really, the uncertainty on the mass model doesn't really manifest as like a significant uncertainty on the source reconstruction.
Okay. I have one question about Euclid. So when do we expect to see the first results on lensing, and in general, how is it going, the analysis?
So I don't know if I'm allowed to tell people this, but the first strong lens in Euclid has been found. I think the time scale, so there's been a couple of delays with things. I think the realistic time scale is we'll probably start to find large samples of lens, or like the actual lens finding will start to kick into gear and start operating and working probably early 2024. And then I think we'll start to really build up the large samples from early 2024 onwards. So in the very near future, I think the data is going to be coming in the next month, and then it's just having the lens finding algorithms run and play out. The one question mark, or the skeptic in me for why I'm maybe a bit worried, like the thing to worry about with Euclid is it's going to find a lot of strong lenses. It's going to find thousands of strong lenses, but it's also going to find tens of thousands of things that look like strong lenses that aren't strong lenses. And it's an open question about how separating those two samples robustly is going to play out, because we don't have color information, we don't have spectra. So I guess I'm just giving a warning that Euclid's definitely going to find lots of strong lenses, but it could take a lot longer to build really robust large samples of lenses.
Cool. Any more questions? Maite?
Hi, James. Very nice talk. And just a silly question. What do you mean by Bayesian inference? So parametrical Bayesian inference? If so, what kind of covariates do you need to model the strong lens with Bayesian inference?
Yeah, so the Bayesian inference sort of comes in different forms of it, come in at different layers of the analysis. If I sort of focus on the source reconstruction as an example, a problem one faces is if you try to, this source reconstruction is basically fitting an image of a strong lens. And if you just allowed the fit to try and do that without any priors or without sort of any basically you should always be able to fit the data perfectly, because you could always put down more Voronoi source pixels. You could basically keep adding more and more complexity to your source until you fitted the data to the noise level. So the Bayesian inference here comes in, where there's basically sort of a penalty term or sort of a framework that As you make the source more complex, as you add more source pixels, as you add more parameters to try and fit the data better, it regularizes the solution and begins to penalize solutions that have more parameters or seemingly using sort of an unjustified amount of complexity in order to fit the data. So, for example, in the analysis, AutoLens could have tried to reconstruct this source with 3 times the number of source pixels and started to fit the data to sort of a much higher fidelity than we see here. But those solutions are actually penalized because the Bayesian framework begins to sort of assess that there's no signal in the data that can justify that complexity. So that's sort of one example of how there's this sort of Bayesian inference underpinning a lot of this strong gravitational lens modeling.
Yeah, thank you.
If there are no more questions, let's thank James for the nice seminar.
Yes, thank you.
And it was really nice to see you, even if at a distance. I think it had been 8 years or so.
Yeah, it's been a long time, terrifyingly. Right, if you're ever in Newcastle, feel free to let us know.
Bye-bye.
See ya.
Bye.